Hey everybody, my name is Levi Weintraub, and if you came here to learn how WebKit renders the web, you're in the right place. So I've worked at a bunch of different companies. I've worked on WebKit at those four, on and off since 2006. Specifically, I started off working on editing. I implemented a bunch of the original exec commands. Then at Palm, I worked on mobile. These days, mostly I do layout and rendering stuff, of which I've done a lot with BiDi and most recently Subpixel. So let's get started. WebKit's a rendering engine, and as you can tell from this super useful diagram, that's like the primary component of a browser. So there's three primary rendering engines. Most of you guys probably already know this. There's Trident, which powers Internet Explorer. There's Gecko, which gives you Firefox. And then there's WebKit, which is obviously what we're going to talk about. And that's a whole grab bag. There's Chrome, Safari, the iOS browser, the Android browser, the Qt browser, BlackBerry browser, WebOS, the Kindle browser. Oh, that's a mouthful. There's GTK. Sorry, the list isn't complete. Those two are free and open source. And of course, Firefox and the Chromium browser are also. Chromium is what Chrome is based on. And WebKit has most recently become the #1 rendering engine on the planet, which is awesome. So a bit about the history before we get into the details. It started off with something called KHTML, which was the rendering engine for the Conqueror browser. It was mostly done by one guy named Lars Noel. And it first shipped in 1998. In 2001, Apple started secretly working on a fork. Then they released JavaScript Core, which was a rewrite of KJS, and that was like the first inkling that they were doing something with KHTML. Then in 2003, WebCore and Safari were released, and it was this giant dump of patch, like with no history. So the KHTML guys were looking at it like, there's no way we can reintegrate this. And it wasn't actually until 2005 that the project itself moved to like opensource.apple.com. So all the revisions were being published. Then in 2007, we got Safari for Windows. 2008, we got Chrome for Windows only. End of 2009 brought us the beta for Mac OS and Linux. 2010, KDE finally started reintegrating those patches back. We also got WebKit 2 announced. And now we're the dominant web platform, and I'm pretty sure Profit's coming up somewhere down the line. So what's the anatomy of a WebKit browser? So first there's the embedding application, which initializes WebKit and pushes it to do work, because WebKit will just sit there unless something is kind of driving the event loop. And it also, funnels user input and URLs, mouse movements, all that into WebKit. Then there's actually a component of WebKit called WebKit. This is a little confusing. And this is where for each port you have your ports interface. So the Apple Mac port looks a certain way in WebKit, and the Chrome one looks completely different. Like they don't really share any code. You get to the actual shared code in something called WebCore. All this is C++. WebKit is sometimes C++, sometimes Objective-C, depending on the platform. So WebCore has the real application logic for a web browser. It handles loading, parsing, layout, style resolution. I'm just reading that you can see. This is, again, not an exhaustive list. And then there are two main components inside of WebCore that it relies on. One of them is this platform layer, which provides abstractions for a bunch of the components that you would expect to change depending on your platform and your OS. This is your network stack, your graphics library, your font engine, wrappers for native widgets like the little glowing buttons in Mac OS. Again, these need to be implemented for each platform. And then there's a JavaScript engine, which in our case is currently only V8 or JavaScript core. And not included here is there's also basically a standard template library that WebKit implements on its own, kind of like the STL. We call it WTF. I'm not even kidding. Web template framework, right? Yeah. So we're mostly going to focus on web core because that's where the actual rendering of a page happens, and we're going to talk about it in terms of flow. So when you start, you type google.com into your browser. It first goes to the loader. And there's a bunch of different loading classes that I'm mostly not going to cover because that's just too much. And it'll start out by kicking off a network request using whatever network engine your platform uses. And then that network connection will call back the loader and say, I have data. And the loader feeds that to the parser. The parser will begin building the DOM tree. And it also will identify sub-resources, images and JavaScript and CSS, anything that's coming from outside the original, URL that you were given. And it feeds those back to the loader to either initiate new network connections or to put it in the queue for processing because you don't want to hammer a website with a million open connections. So prior to HTML5, there was no spec for parsing. Now there is, thank God. So there's actually a consistent way. But before that, if you had badly formatted HTML, you really never knew what you were getting. So then we get into the DOM tree. This is where things start to get interesting. Now the DOM provides an API to JavaScript. It also will begin building the render tree. It's a full representation of the document. Everything that is happening there is in the DOM tree. You could actually stop here, basically, and not even worry about the render tree that we're going to get into, because this has all the information that you need. It also has something called the shadow DOM that we'll get to at the end. So here's an example of what you'll get from some sample markup. You'll see that the things on the right are actually the WebKit class names for those sorts of that sort of markup. So there's always an HTML document, so we're not talking about exactly a one-to-one relation here. And in fact, the parser can insert objects into the DOM tree if you have malformations to try to fix up your markup. But you'll see there's something called a text node, which foo becomes text foo. A div just becomes HTML div element. The names kind of follow what you'd expect. So then there's the render tree. And the render tree only, well, let's see. Render tree, why not render forest? Because it's really not one tree. These are the primary structures, and again, not even close to exhaustive. There's something called render objects. We'll cover all these individually. There's layers, there's inline boxes, and there's style. So let's start with render objects. They are directly owned by the DOM tree. So you can, from within WebKit, you can query a DOM node for its renderer and vice versa. There's not necessarily a one-to-one correlation. Again, for things like continuations, if you split an inline, you can have multiple renderers that report back to the same DOM node. They only exist for rendered content. So if you say display none, you're effectively destroying that section of the render tree. Or if it starts that way, it'll just never be created. We also use something called arena allocation to try to make building and tearing down the render tree as fast as possible to minimize allocations here. Because render objects come and go as you move things around, whatever. So render objects are responsible for layout and paint. When you ask, what's the offset left or offset top of an element, that DOM node queries its renderer object for that answer. So here's another example. There's some sample DOM. And again, those are the actual class names in WebKit for the render objects that would be created. You can see that they're no longer quite as similar to the markup as they used to be. HTML div element becomes a render block, but so does HTML body element. And HTML span element becomes a render inline. These can change depending on how you say display, right? Display block will become a render block. Display inline will become a render inline. And you'll see that even text gets a renderer, which is a render text. There's also a concept of anonymous renderers. You'll see this a lot in tables, but also just as something as simple as having a div or a block flow element with some text and a div in it, another block flow element, to make layout substantially easier. Block flow elements, according to the spec, can only have either block or inline children. And in the case that they don't, which is pretty often, an anonymous block renderer is actually inserted into the render tree so that that green render block only has to lay out block flow children. And again, for tables, you'll see this a lot. If you don't put a table body in, one will get inserted. So then there's the style tree. So there are these things called render styles. They contain the computed style of every render object. And they're owned by the render object tree. And render objects share them a ton because on most web pages, there are going to be tons and tons of renderers that have very similar style. I mean, you can imagine if you say that all divs have one certain, like border around it, then they can all share one render style. Render styles also share data members because there are tons of styles that are inherited, and so to try to save memory, there's some really awesome logic in there that takes care of that. Which means when you're inside of layout or rendering code, you can't just take the render style associated with some render object and change one of the values because you might end up changing it for dozens of other unrelated elements. So there's a whole pass where computed style resolution happens before we even get into layout. Or reflow if you're talking to Mozilla folks, but we'll get a little bit more into that. And then there's render layers. A lot of people have heard about these now. It's kind of like a Swiss Army knife for the render tree. There's always one per document. The root always has one, but it's also used for video, canvas if it has a 3D context, which is WebGL. Anything that's relatively absolutely positioned or fixed, anything with a transformation, anything that's transparent, masked, clipped, scrollable, reflections, all of these things are taken care of by the render layer tree because effectively it allows us to make render objects pretty dumb. They don't have to know about a reflection because if they have a reflection, they'll have this render layer associated with them, which will effectively set up the graphics context before handing it off to that render object already set up to do reflection. So they're also used for stacking contexts. So it looks kind of like this. Render objects don't always flow the same way the DOM does. So if something has a layer, they're seated inside of that layer in the layer tree. And each render layer has two ordered lists, one of the negative z indexes in order and one of the positive. And this is so we can handle things like painting and hit texting. So in painting, we start with the negative z index and we paint through that from the most negative towards 0. Then we paint ourselves and then we paint through the positive. We do the opposite for hit testing because whatever is most positive is obviously closest to the front. And this is kind of legacy for software because when we paint using software rendering, which we still do, just not always, we end up rendering to one buffer. which means there's one region of memory that's eventually going to get blitted to the screen. So to make your page come out right, we have to start effectively from the back and paint our way to the front. So the way WebKit usually gets called is it gets calls with a dirty rectangle. So we fill in that dirty rect. We intersect each one through all the render layers, everything that intersects it, we paint, and then we eventually hand off the completed buffer, which will have in the correct order, the image that we were looking for. So obviously you knew this was coming. So in today's world of hardware accelerated graphics, we also sometimes use it, right? So not all render layers have a backing store, which is a GPU texture. If you want one of those, you need to have a 3D transform or a 3D canvas or 3D plugin. Stacking contexts or subframes will also get these. Now, why bother? When we're doing accelerated compositing, we end up using a lot more memory. Every texture is only one part of the completed output buffer, whereas with software, we'll never reserve more memory than what we can see on the screen. But now we're talking, if you have one 3D transformed element, you're going to have a texture associated with that. So that inevitably means more memory. But when we scroll, we don't have to repaint the whole page. If things aren't getting dirtied, we don't have to repaint those textures. Plus, for things like transparency, the graphics card is excellent at compositing something that's partially transparent, whereas with software, you have to repaint every pixel. And you have to go through the whole set of render layers every time you do that. So this can vastly improve scrolling, but you got to keep in mind it's at the expense of memory. So line box tree, I've spent a lot of time in there. It's owned by the render block. There are these things called root inline boxes, one of which there's one per line, and that owns all of the inline boxes that are within those lines. So every inline is associated with, every render inline, I should say, is associated with one or more inline boxes. And every inline box has exactly one render object. But if render objects were dumb, inline boxes are even dumber. They don't own their own style. They can't handle their own layout. They rely on the render block to do their layout, and they rely on their render object to tell them what color they are and if they have a border. But and that's important because, again, depending on how lines wrap, you can end up with many inline boxes for one render object. So here's an example. The markup's at the top, and you can see an example render tree on the left, and you can see a line box tree on the right. So the render block isn't in the line box tree. It's just there as an example. But then you can see that because there's a BR in there, we have two root inline boxes, one for each line. And you get an inline text box for your text nodes. You get an inline flow box for things like a B tag or a span. And then you get just a generic inline box for a BR, which you need to know that when you're running through the render block line layout code that you need to break there. So now let's talk about layout. Layout is done lazily. You can kind of think of the entire set of render trees as a cache. Once again, the DOM tree has all the data you need to actually paint a page. It has all the style, it has all the elements. But if you tried to read that through every time you wanted to paint a frame, you'd be going really slowly. So instead, there's all these things are just caching where things are and what they look like to try to speed up painting. So we avoid going through layout and trying to figure out where things are as much as possible. So when something changes, when you change a style, when you move something around, when you insert a new DOM node, we mark parts of the render tree as dirty. And before we ever paint, or as soon as you request some sort of information from the render tree, which is offset top, offset width, then we perform a layout. So the first thing we do when we do that is in each element we'll save our dirty rect, or sorry, our old repaint rect, so that when we get to the end we know what to repaint. Because if we moved, we have to not only paint ourselves at our new location, but we have to clean up our old one. So we save our dirty rect, we bring in any updates from the DOM. This is where style resolution happens. This is also where render objects are created. And then as we go through here, each render object will determine its preferred width, and then it will lay out its children. And you can imagine you check your child, see if it fits next to the previous one. If it doesn't, it goes down to the next line. So that's how we figure out our height. As we push these things in, knowing our width already, we can figure out how tall we are. And then eventually we'll end up with our new repaint rect, and we send the new and the old off to our embedding application and say, these are dirty, repaint us. Avoid extra layouts. You want to set all style that you're going to change in like execution of JavaScript before you ask for how wide or something is or where it is. Because if you do that, say you're setting style, reading back values, setting style, reading back values, you're going to do a lot of unnecessary work because you're going to be triggering layout every time you ask for something. And if you're dirtying it in between that, we could have taken care of all that in one pass if you properly set things up. Same goes for detached DOM. Do as much work in a detached DOM as you can before inserting it into the document, because that'll allow us to coalesce this sort of work into one operation, which is much faster. So line layouts. The first thing you do when trying to lay out a line is determine the left and right. To do this, render block will have a red-black tree that tracks all the floats that intersect it, and you search with the range of this line to determine what floats that line is going to intersect, and then you can determine your left and right, and obviously what's in between is your width. So then we start reiterating over both characters and inlines. Why both? Because inlines can take up space if they have borders, but also they can have influence for bidirectional text. So we have the structure that keeps track of committed and uncommitted width, and you can kind of think about if you have several words and you're only breaking on spaces, for example, once you've read an entire set of characters of a word and you check to see if it can fit on that line. If it can, you can commit it, and then you start reading the next set of characters to read the next word to see if it will fit. So we used ICU and font measurement to determine where we're going to break the lines. As we read our characters, we add up, the amount of space to the next place that we could potentially break the line, which is what ICU tells us, and then we see if it fits. If it doesn't, we push it down to the next line. In this process, we're also creating these things called text runs, and then on each line, we go through something called the Unicode bidirectional algorithm, which will flip these text runs back and forth, back and forth, back and forth, and this is for bidirectional text. If you never have Hebrew and English in one line, you never have to actually worry about this. So to review, loader, parser, DOM tree, render tree. And the render tree has, and again, these are the class names for the base classes of these various render trees: render objects, render layers, render style, and inline boxes. So painting. All kinds of things can trigger repaints, right? Animations, blinking caret, obviously layout and style changes, So what we do when we get those is we find the rectangle that has been dirtied, and we pass that up to the embedding application. And it's actually the embedding app's job to coalesce these as it will, and then push WebKit to repaint it. WebKit can't repaint itself. And as we've discussed, is this tree walk from the render layer, from the root render layer, to do a repaint. And then it passes through the only things that actually do painting are render objects and inline boxes, nothing else. And there's this thing called the graphics context, which is again the WebKit class name, which is an abstraction of whatever your platform's graphics library is that can do basic operations like drawing a line, drawing text, doing clipping, everything like that. And that lives in the platform code. And then hit testing. So in a browser, you're constantly hit testing if you move your mouse. There are also multiple phases of hit testing. So if you're just moving your mouse, you only care about the backgrounds of elements. You don't care if you're hitting the text or not, really. When you're doing selection, you care specifically about the foregrounds. As we say, again, you start in the root render layer, but traverse the opposite direction as paint. And hit testing, kind of like painting, the render objects handle this, but they're dumb. They don't know about transforms. So render layers will handle transforming whatever that position is into the local coordinates of that render object. Now we're going to cover a few things that are coming up, starting with something called the component model. So the component model is based on the shadow DOM, so maybe we should talk about what the shadow DOM is. Shadow DOMs have been around for a long time. Anybody who's worked with forms, at least if they've been working on it for a while, has seen a text area. And if you look at a text area from just the DOM API, there could be a ton of text in that text area, but you can't see it. There's a DOM API for getting the text out, but there's no child of the text area, unlike anything else that has text. Well, the reason for that is it allows us as browser vendors to hide away the actual implementation of that control, which would be kind of nice for a web developer, right? Some sort of encapsulation. So that's what the component model is all about. It allows you to basically take advantage of something that we've been doing for a long time internally, and use it to build components that you can pretty much guarantee will play nice with the surrounding web page without having to use an iframe, which is really heavyweight. So what does it do? It retargets events. So if an event originates from inside of the shadow DOM, when it gets to the shadow boundary, it'll be retargeted to that node so that nobody from the outside can see where that event originally came from. And also the shadow children are inaccessible by the regular DOM API. So when you're traversing the DOM, you won't see what's in there. It also allows you to define an interface. So say you have some button and it's got a bunch of different elements inside of it. But the only thing you want somebody who's consuming your button to be able to do is push it. Well, you can then define that there's like an operation on your component called push, and that's it. And they can't mess with anything else. So how does it work? So there's something called the shadow host, and it can have children in the DOM, just like a text area. You can insert children into a text area, but you never end up seeing them. Instead, there's this thing called a shadow root, which exists beyond this shadowy boundary. And it represents that shadow host inside of this evil shadow world. and it has its own set of children. And so when we go to actually render, and we'll do this one more time, we get rid of the original children and paint the shadow children underneath. So again, although the regular DOM will let you see the actual DOM children of that shadow host, when you actually interact with it, or at least in the rendering tree, those guys don't exist. And nothing you do can make them be visible. Next I'm going to talk about something that I've been working on for a really long time. So WebKit is the last major rendering engine that still does all layout on integers. And I say this even though this project is kind of almost done now, thank God, if you're running a really new Chrome dev build. Anyway, it uses integers, which represent pixels, which kind of makes sense because ultimately we're going to render on pixel boundaries. So when there's a fraction of a pixel, we truncate. Well, that's only a problem when you start zooming, for the most part, but it allows error to accumulate. So if you truncate, one object, the most you're going to be off by is 1 pixel, right? I mean, you multiply, by 1.5x, and you'll get some remainder, but it will only be 1 pixel. And anybody who's been trying to do pixel perfect web pages already knows that it's almost impossible anyway, right? So 1 pixel, fine. But especially with 1.5x zoom, if you start stacking things, it's a problem. So here we have a red box that's 1 div, and it's 150 pixels tall at a 1.5x zoom, which, if you do the math, is 225 pixels. But the green boxes are a stack of 10 divs that are each 15 pixels. So 10 divs, 15 pixels each, that should be 150 pixels as well. But when you multiply it by our 1.5x scale, and you truncate each time, because remember, we lay out one render object at a time, and each one of those will end up being 22 pixels, so you'll be off by 5 pixels, which can look really bad. And there's really no limit. I mean, the more objects you stack, the more your error can accumulate, and the worse things will get. So we call it subpixel layout, which a lot of people confuse with subpixel rendering, which it is not. Because when you ask for a 1 pixel wide border, you probably really want 1 pixel wide border, not a 1 pixel wide border in between 2 pixels, so it'll be anti-alias to 2 gray pixels if it's supposed to be black. So we use a fixed point unit. Fixed point isn't actually exactly right. Basically, you use an integer that represents 1/60. So it's a 60th of a pixel instead of a full pixel. This is actually the same value that Gecko and Firefox use. Internet Explorer uses different ones depending on the DPI of your screen. It also allows us to support sub-pixel CSS values, which is nice if you want to over-specify your page so that when you zoom in, things continue to look like how you'd expect them to. And error doesn't accumulate, or at least accumulates much, much slower, right? So another cool thing coming up, mostly done by our friends at Adobe, is something called CSS regions, which lets you thread one set of text and images and inlines through multiple blockflow elements. It also allows you to have your style be for sections of the page instead of exactly one set of content. And it also, part of this same spec includes shapes and exclusions. So just real quick, threading means this one set of text, when it gets to the end of one section, will just move to the next place that's been defined to be included in this region. You can kind of imagine it allowing you to do magazine-style layout. It also allows you to do things that'll change with form factors much nicer than traditional HTML and columns. Also shapes and exclusions. You can define arbitrary polygons, and you can either have text and images flow directly through those or around them. And that's mostly what we're going to say about WebCore, and I'm just going to wrap up here with a bit about the current state of browsers, because what I explained at the beginning is really the old single monolithic process. So these days, we're seeing more and more browsers use multiple processes. The primary reason is for safety through sandboxing. You can run the renderer, which is basically loading arbitrary code from the internet inside of a sandbox with much lower priority, not priority, abilities, right? And that allows you to not worry so much about the renderer being compromised, which happens with some frequency on all rendering engines, and instead you don't have a true exploit or you don't have the user at risk unless they also manage to elevate their privileges to the overarching browser app or browser process, which is much more rare. It also allows you to centralize your resources. So you can have one compositor, you can have one instance of Flash for a bunch of different renderers, and multiple main loops. It's almost like multi-core, right? Which is kind of nice. It's close enough. Here's an example of what Chrome kind of looks like. There's one browser process which owns all the other processes. There's one GPU process which is shared by the browser and all the renderers. There is one plugin process per plugin, and then there are a bunch of different render processes. Those are what actually run WebKit and V8, and it's not one-to-one. Not every tab gets gets its own render process. Often they're shared by the same domain, but not always. There's a whole complicated set of rules, and we also limit the number for memory usage depending on how much memory you have. And one of the cool things that happens here is the render processes, when they're doing accelerated compositing, actually output GLES 2.0 instructions into a shared piece of memory and the textures, and the GPU process can then consume these just in a row, and that allows, say, the Chrome for Android thing to ignore the GPU process, do everything in process, and just consume these GLES 2.0 instructions directly, because that's what most mobile phones already use. So there's basically one accelerated compositing pipeline for both mobile and non-mobile, which I think is really cool. And that's it. Now I'll answer any questions if you guys have any. You.
I do a lot of animations, and so Safari and Chrome, both use WebKit, of course. But it looks like animations in Safari are far smoother frame rate than Chrome. Is there any particular reason why that might be?
The question is, why are animations in Safari faster than Chrome? Smoother than Chrome. I mean, there's the multi-process thing comes with some overhead. We don't get to write directly to the screen, for example. We have to marshal all repaints through IPC, inter-process communications, right? Which again comes with some overhead. For a long time, we weren't using the native animation framework for. I'm guessing you use Mac OS. Is that right? Yeah. I do believe we now do. So that might change. But in general, these are things that are always being improved. By they I mean Apple came out with the initial implementation of accelerated CSS animations. So to an extent, there was some catch-up involved.
Oh, so it's not the same for each browser?
Well, no. So Chrome uses Skia, for example, which is a graphics library, and it uses it on Mac, Linux, and Windows, whereas the Mac port uses Core Graphics and actually has a port of Core Graphics to Windows last that I checked. So they are using very different platform bits, basically. And they also use, like I said, Core Animation is another part of Mac OS that I don't know if we use, or if we use now. I think we do now, but I don't know specifically. Questions? More? Who's got them? How is it rendering a block that has a new what context? What do you mean formatting context?
It seems back it doesn't clear floats, or rather, it will clear floats, and if something's floated to the left, it will wrap around it, it stays in it, and it also tracks markers.
Boy, I'd have to think about that one for a while. Stump the chump. We could talk later if you want. Over there.
I have a handful of questions. I'll start with
Do you want to grab that microphone? That way I don't have to repeat them all.
Hello. Okay. So I have a handful of questions on graphics specifically.
On what?
Graphics.
Okay.
So the Canvas 2D acceleration, or just Canvas 2D APIs, are completely implemented in platform layers today, which is, as you explained, macOS has a completely different performance that you see, and this is like magnified when you go into the mobile platform, right?
Sure.
The iOS browser, for lack of a better word, kicks ass. The Android browser really struggles when you do animation and stuff. My question is there any effort going on to have a common 2D graphics context that is accelerated, either via GLES2 or something else? Wouldn't it benefit all the ports instead of having these at the porting layer, which is a real nightmare?
So we're still talking about 2D, right?
Correct.
Okay. So there's definitely nothing like that in the works now, and it's really just for lack of interest, I think. So I mean, Apple wants to use core graphics. Android and Chrome on Linux, for example, they can't possibly use core graphics because it's all proprietary. That makes things really tricky. Ski is open source; they could totally use it. But I mean, like you said, if they're kicking our ass right now, why would they, right? Ideally, that stuff should all be transparent, and there's certainly an effort to try to make any differences or discrepancies with rendering between the different platforms go away. But whether or not they settle on the same back end, you should have no idea. And really, if it's just a performance thing and we're lagging, we just need to get our act together and fix it. Have you tried the newest Chrome beta for Android?
Actually, I have the stock Google phone.
Is it better?
It's better than the stock browser, but it still lags.
Still lags.
Many of the tests. I think it depends on the tests that you run. So on the WebKit page, there is a falling leaves demo.
Yeah, I know that one.
That one runs pretty badly on Chrome. But
Got
I
it.
have a bunch of other benchmark tests that I have. Some of them run well, some of them don't. One more question on when you're talking about text rendering, what about hyphenation? Again, this is one of those features that works on Safari, but not on Chrome, even on the desktop version. Yep,
that's right. So, I mean, hyphenation, again, uses basically ICU, right? You use some other library that understands where things can be hyphenated for different languages. And there's a few of those. And by those, I mean libraries that do this. And Mac OS and Windows both have ones built in that do it slightly differently. And it's just, for Chrome, it just simply hasn't been implemented. It's actually like on my really, really, really long list of things that would be fun to work on. Not that I'm there yet. The code to support it exists. We would have to settle on, well, I mean, basically we'd have to re-implement it depending on the platform or find some platform agnostic library that does this. And I don't know if that specifically exists yet, which means the barrier is kind of high. One of the nice things that Apple has going for it is if they have their own hyphenation library, they can also basically port it to Windows, ship it with Safari, and reuse the same code. We don't necessarily have that same benefit. Oh, okay, I guess that's it. Thanks for coming.